Okay, let's have a think about atomic size then. So there's a lot of this theory that can be applied to all the other groups. We're obviously going to apply it to the context of group 7, but like I say, the theory is the same across the groups most of the time. So in this case, atomic size, moving down a group of the periodic table, atomic size will always increase. So this is across the board. As you go down group 1, group 2, we'll ignore the transition metals for now, group 3, group 4, group 5, group 6, group 7, group 8, the atomic size will always increase. If we plotted the halogens, the first 4 halogens on a graph against atomic radius, so that's radius is from the center to the outside of an atom, then we can see that they get bigger. So we start off small, getting a bit bigger, getting a bit bigger, getting a bit bigger. So that's our atomic radius increasing. There we go. Why is this then? As you go down a group, why is there increasing size? Have a think. I will just say, again, one of the things that makes memorizing some of this content or recalling some of this content hard is because lots of places will show you all of the trends in terms of increasing. Lots of places will show you all of the trends in terms of always going from left to right across a period and top to bottom down a group. And because of that, sometimes your trend could be increasing, sometimes it could be decreasing, or sometimes you could be going bottom to top up a group because you're always doing increasing. It just means the trends are always the same, but the way that you're told to remember it or the way it's introduced to you might be the opposite to the way that you started memorizing it. It's one of the things that makes chemistry really difficult. I will do my best to always talk about trends going from left to right across a period. So they could be either decreasing or increasing across a period, left to right, and down a group always. I will do my best so that it's consistent, but just bear in mind you may have been taught it in terms of always, where does the increasing trend go? Does it go from right to left, or does it go up the group if it's increasing? So just bear it in mind. It can be confusing, and sometimes we do mix the two up. What else did I want to say? Oh yes, so why is it increasing in size? It's increasing in size because as you go down period, one of the links to the periodic table is every period, so 2, 3, 4, 5, etc., you are adding a shell of electrons. So moving down a group of the periodic table, atomic size will always increase as we are adding another shell of electrons. So E minus, I'm just using as electrons because I'm lazy. In an exam, please write it out as the full word electrons, but I'm just being lazy for now. Electrons, so we're adding another shell of electrons for each period. The period number tells you the number of shells of electrons in that atom. Okay, let's have a think specifically. So here we've got fluorine, bromine, and iodine. We're thinking about single atoms of these rather than them when they're in their molecular elemental state. Fluorine has got 9 electrons in total and is that size. Chlorine has got 17 electrons in total and is that size. Bromine has got 35 electrons in total, and iodine, I can't actually remember how much it's got. We'd never be asked to draw iodine though. Oh, actually, to be fair, iodine gets confusing, so we'll leave that for now. Okay, lovely. And where are their outer electrons then? Where are the outer electrons? So for the first 3, those are the ones you might be expected to write the electron configuration for. So actually, you're unlikely to be expected to write the electron configuration for bromine, I don't think, but you might, so we'll keep practicing. So where are those outer electrons? All of these are what we call p block elements because their outer electrons exist in a p orbital. So all of these have their valence electrons in p orbitals. So if we were writing out the electronic configuration, fluorine's outer subshell would be 2p5. Subshell notation would be 2p5. So 5 electrons in the p subshell in shell 2, the second p subshell. Chlorine would be 3p5, bromine 4p5, iodine therefore 5p5, but we'll leave that one for now. So we can see every time we're adding a shell of electrons, that is increasing the atomic radius. Why? Just have a think, we'll come back to it later, but why is the atomic radius increasing when you add a shell of electrons? As well as the electrons being added further out, why are they added further out? What's happening between electrons that are present and ones you're adding that means that they sit further away? Just have a think. We'll come back to it. Okay, what about going across a period? As we go across a period from left to right, this is left to right, atomic size decreases. Let's see what that looks like. So as you go across from left to right, there is decrease. Oops, that doesn't look like a word. Decreasing size. Atomic size decreases. And you can see that, for example, as we go from lithium to neon, from sodium to argon, you can see the atomic size decreases. You can even see it from hydrogen to helium. We have a decrease in size as you go across the period. So why is that? Why? We've just looked at when we're adding extra electrons, it gets bigger. So why, when we're adding extra electrons here, is it getting smaller? This is something that confuses lots of students. It's because as we go across, as well as if you're going from one element to the next element, as well as adding an electron, we're also adding a proton. And the effect of adding a proton, because protons are positive and the electron is negative, the effect of adding the proton pulls in the other electrons a little bit tighter. So moving across the period, atomic size decreases as we are adding an extra electron. Or no, let's say it differently. As we are increasing the number of protons, let's say it like that. Increasing the, again, I'm going to be lazy, no number of protons. But we are adding the electrons into the same shell. If we're adding the electrons into the same shell, adding the electron into the same shell as previously, I'm going to write there, the same shell. If we're adding it into the same shell, then that shell is already being provided with shielding. We're not increasing the amount of shielding because the electron's going into the outer shell. If the electron's going into the outer shell, then it's not going to be adding any shielding. So by adding the electron to the same shell, so there is no added shielding. If there's no added shielding, but we've added a proton, the electrons are pulled in tighter. Electrons are, I'm going to say held in tighter, but you can also say there's a greater attraction between the protons and the outer electrons. Hence, the atom is smaller. Okay. One thing that you can see really beautifully as well, sorry, in this graph is just the jump up when you add a new shell. Because the outer electrons now have shielding, are now being shielded by a layer of electrons effectively between them and the proton. So you can see there as well, and there's a new shell added, so there's increased shielding. The other way to think about it as well, just to link back to our the slide before, is the shielding, as well as being kind of a shield, a layer between the outer electrons and the proton, it's also repulsion. If I'm adding electrons to the outside, I know that the orbitals are not technically within rings like we think about them, but if we're adding an electron to the outer shells, there's added electron repulsion. And that is going to cause the size of the atom to increase as well, because the electrons are going to be repelling. Although the outer electrons are attracted to the nucleus, they're also going to be repelling the inner electrons as well. There's another way to think about it, another way to help understand the theory. Okay, let's have a go at some exam questions. Oh, there's a fly. So this says, state and explain the size difference between fluorine and sodium atoms. Atoms, not molecules. So context, I'm thinking about size difference between atoms, so that's structure and bonding. State and explain the size difference. So my command word is state and explain. I've got 2. So the likelihood is we're going to get this 3-mark question. So we're going to get 1 mark for the statement and 2 for the explain. It's important to think about that because you want to make sure that your explanation includes 2 markable points. If you've only given 1 part of an explanation, you can only get 1 mark for the explain part. So you'd lose a mark. So make sure that your explain has got 2 parts to it, or 2 awardable pieces of information. So state a simple answer, explain, give reasoning. And then specifically, it's between fluorine and sodium. So why have they asked us this question? It's another example where we can think, why would they have asked us this question? Fluorine and sodium. Think about where fluorine and sodium are on the periodic table. So why have they asked us this question? Why is it important or interesting? What answer would you give? Have a think about what answer you would give here. And then we will have a look. I'll give you 10 seconds or so while I take a drink. The other thing to note as well, actually, I'll say is questions like this are usually expecting you to compare the 2 atoms, and therefore you need to think about using comparison words as well. Now, often they'll use the word compare in their questions, so compare the size difference between fluorine and sodium, and in which case you need to definitely make sure you're using comparison words. So things like bigger than, or more than, or whatever. So you can't just say that there are a large number of, because that's just a statement of something on its own. You have to say that there is more than, so that it's a comparison between 2 things. Anyway, what would we say here? So something like this. So if we're looking from fluorine to sodium, we would be thinking about our increase in the number of protons. So as you go from fluorine to sodium, there is an increase in the number of protons. This is going to draw the electrons in tighter, or you can say the attraction between the protons in the nucleus and the outer electrons will be stronger, or there will be a greater attraction. There's an increase in the number of electron shells as well. So we go from fluorine down to sodium. We've added an electron shell. That means there is greater shielding. You can also talk about there being greater electronic repulsion between electrons, but shielding is usually the word they're looking for in an exam, the word shielding. Overall, the electron repulsion effects, so the shielding, is greater in sodium, which causes an increase in its atomic size. Compared to fluorine. So that's our comparison in there. 3 marks available. The first mark is to state the size difference. So we've actually put that in our final sentence, which is fine, where we've said it causes an increase in its atomic size compared to fluorine. So that's our first mark, or a mark. Then 2 marks for the explanation. You'll notice that we've got the what's the word? We've got the, we're looking at both sides of the arguments here, because both sides are important. There's an increase in the number of protons, which draws electrons in, but actually we've said that the atomic size is increased. That's why this is a 3-mark question and not just a 2-mark question, because you've got these 2 conflicting ideas. The idea that you're adding protons, so that's going to draw them in tighter, but you're also adding electron shells, so that's going to allow an atom to be bigger. And so 1 mark will be for stating both of those facts. The increase in the number of protons draws them in tighter, or would make it smaller, but then you've got an increased shielding, which allows it to be bigger. And the second mark, for the explanation comes from the fact that we've said the electron repulsion effects, or the shielding effect, so you could have said shielding there, effects are greater. If they are greater, if they have more of an impact on the size, then that's what causes the difference in size. So we've had to say both sides of the argument, but we've explained which is the dominant factor. Okay, let's keep